What is Sumcheck? In this video, we're diving into the Sumcheck protocol, what it is, how it works, and where it's used. Sumcheck is a type of IOP. But what is an IOP? IOP stands for Interactive Oracle Proof, which is a protocol between two parties, a prover and a verifier, where the prover tries to convince the verifier that some statement is true. For simplicity, let us assume that the statement is a solution to a problem known to both parties. The simplest way to convince is for the prover to send the solution to the verifier. But this has two disadvantages. The first disadvantage is that the solution may be long. Since the verifier only needs to know that the solution is correct, it makes sense that maybe there's a more succinct way to portray that information only. The second disadvantage is that many times the prover wants to convince the verifier without disclosing the solution. Providing the solution is not helpful in those cases. An IOP relies on two things. The first is the oracle, which is an agreement between the two parties. We can think of the oracle as an agreement on the joint problem being solved. The second is the interaction between the prover and the verifier. The interactive question-answer protocol allows the verifier to repeatedly refine her questions. Remember the game 21 questions? It's exactly this. What does Sumcheck actually prove? Imagine the prover and verifier have a list of numbers, and for some reason, the verifier wants to know the sum of the numbers in the list, but cannot perform the sum herself due to computational limitations. She can ask the prover for the sum. But how can she believe him if she doesn't trust him? The Sumcheck protocol is a way for the prover to convince the verifier of the true sum that doesn't require the verifier to compute the sum herself. The protocol provides two guarantees. First guarantee is that if the sum is correct, the prover always succeeds in convincing. The second is that if the sum is wrong, the verifier will be able to catch the lie nearly every time. Can we make this more concrete? Take a list of n numbers, y0 to y at n-1. For simplicity, let's assume that n is a power of 2 and that n equals 2 to the power m. We construct a polynomial, g, of xm to x1 that evaluates to our list of numbers when the variables, the x's, are all zeros or ones. For example, g at 0, 0, 0, etc., 1, 1, 1 equals y at index 7, because 7 in binary representation is 0, 0, 0, etc., 1, 1, 1. We make sure that the polynomial g is a multilinear extension, an MLE, which makes it uniquely defined by our list, y0 to yn-1. Loosely speaking, we're relying on a famous lemma called the Schwartz-Zippel lemma that provides two assurances. Firstly, it assures us that our MLE is unique for our list. Secondly, it assures us that evaluations of two distinct MLEs will differ nearly everywhere. To get the seventh index of the list, y7, we evaluate the polynomial at 0, 0, 0, etc., 1, 1, 1. The prover commits to the polynomial and sends the commitment to the verifier. The commitment allows the verifier to confirm evaluations of the polynomial on its own. We refer to the commitment as the oracle. The verifier can now ask the oracle for the evaluations of g for all input x sequences that have only zeros and ones, and sum them as g at the all zeros plus g at 0, 0, 0, etc., 1 plus etc. But this is exactly like summing the list y0 to yn-1, and as we said before, the verifier is computationally unable to do this. Instead, the verifier asks the prover for the sum and then asks questions that lead the prover to provide her with an evaluation of the polynomial g at a random location. G at Rm to R1, where the r's are random non-binary numbers. The verifier checks that what she received from the prover is consistent with the oracle. If it is, she accepts the proof and is convinced. If not, she rejects the proof. How about an example? Take a list of 4 numbers, 1, 2, 3, and 5. The length of the list is n equals 4, and n equals 2 to the power 2, so m equals 2. The sum of the list is 11. We construct an MLE that evaluates as follows. First, we set the list as the following evaluations. G at 0, 0 equals 1. G at 0, 1 equals 2. G at 1, 0 equals 3. And G at 1, 1 equals 5. Then the MLE is G at x2, x1 equals 1 times 1 minus x2 times 1 minus x1 plus 2 times 1 minus x2 times x1 plus 3 times x2 times 1 minus x1 plus 5 times x2 times x1. Note that if we plug in any index x2, x1 from 0, 0, 0, 1, 1, 0, or 1, 1, the terms unassociated with the index get cancelled out, leaving only the relevant evaluation. Try it for yourself. Now if we collect the terms, we get that g at x2, x1 equals 1 plus 2 times x2 plus x1 plus x2 times x1. The Sumcheck protocol proceeds as follows. The prover claims that the sum is s equals 11. Then he sends the single variable polynomial g1 at x1, which equals g at 0, x1, plus g at 1, x1, which equals 4 plus 3x1. The verifier verifies that g1 at 0 plus g1 at 1 equals s, which equals 11. Then she sends a random number, say r1 equals 3. The prover sends the single variable polynomial g2 at x2, which equals g at x2, r1, which equals g at x2, 3, which equals 4 plus 5 times x2. The verifier verifies that g2 at 0 plus g2 at 1 equals g1 at r1, which equals g1 at 3, which equals 13. Then she draws a random number, say r2 equals 7. She calculates g2 at r2, which equals g2 at 7, which equals 39. Using the oracle, she verifies that indeed g at 7, 3 equals g2 at 7, which equals 39. This completes the proof. But why do we care about proving sums? Let's try to explain this using one simple example. In this example, we illustrate how to map a general computation to a sumcheck. This process is often called arithmetization. There are many such mappings, but we will show one just to illustrate the usefulness of sumcheck. Say you have two input sequences, in 11, in 12, and in 21, in 22. And an output sequence, out1, which is equal to in 11 plus in 21, out2, which is equal to in 12 times in 22. The prover wants to use Sumcheck to prove that the output-input relationship holds without requiring the verifier to actually compute and verify everything. In our example, the inputs and outputs are very small. But imagine they were much, much larger. The prover can do the following. 1. Construct the following three polynomials. In1 at x equals in11 times 1 minus x plus in12 times x. In2 of x equals in21 times 1 minus x plus in22 times x. And finally, out of x equals out1 times 1 minus x plus out2 times x. The second step is to construct two more helper polynomials. Ed of x, which is equal to 1 times 1 minus x plus 0 times x, and mult of x, which is equal to 0 times 1 minus x plus 1 times x. The purpose of the helper polynomials is to indicate when we want to add and when we want to multiply. They are sometimes called equality polynomials or indicator functions. The third step is to assemble the five polynomials to the following equation. Ed of x times in1 of x plus in2 of x plus mult of x times in1 of x times in2 of x equal to out of x. Note that this equation covers the original relation that the prover wants to prove. In the fourth step, we'll rearrange the equation as ed of x times in1 of x plus ed of x times in2 of x plus mult of x times in1 of x times in2 of x minus out of x equals 0. This is a Sumcheck instance where the sum is 0 and is sometimes called a zero check. Finally, the prover can construct the five polynomials and commit to them. Then run a Sumcheck protocol to prove that the polynomial adds to 0. Let's look at a practical example of where Sumcheck is used today.
Jolt is a zero-knowledge virtual machine, or ZKVM, that allows developers to write high-level programs with verifiable proofs of computation, running efficiently and easily in any language that compiles to RISC-V assembly. Running computations in a decentralized environment is extremely expensive. Historically, blockchain networks have managed to decentralize validation power by requiring each participant to re-execute the same work, resulting in massive waste. Succinctness allows a single party to compress the validation work on behalf of the network without reducing decentralization guarantees, increasing network efficiency and performance. Utilizing the Sumcheck protocol in Lasso, Jolt efficiently validates computations off-chain and generates succinct proofs that are easily verified by the network. Sumcheck is an extremely efficient IOP that can take advantage of small commitments, minimize prover overhead, and reduce communication costs. These components make the protocol an ideal choice for blockchain networks. For more details on these innovations, check out the research papers and blog posts by A16Z in the description below. They provide insights into the technical evolution and performance benchmarks of Lasso and Jolt. Also be sure to watch our video, The Magic of Zero-Knowledge Proofs, for a deep dive into how ZK proofs work. Thanks for watching.